Proper understanding of how a pressure balance determines pressure can ensure that it is used in such a way that is both sufficiently accurate as well as efficient. Depending upon the design, the physical operation of the unit can be relatively straightforward. You simply set the necessary mass on top of the piston and increase the pressure under the piston until it is floating. At that point, you will have a stable pressure that is a function of the amount of mass used and the area of the piston, along with a number of other factors. These factors result in a somewhat complex mathematical equation. There are many factors that impact the pressure, and if not accounted for, they can result in bad measurements taking place. When using a pressure balance, there are two extremes in the approach you can take to determining the pressure. The first extreme is to measure each variable that impacts the pressure and perform a full calculation of the fundamental pressure equation. This is the approach used on high-end piston gauges like the Fluke Calibration PG7000 series. By using this approach, with the right equipment, it is feasible for one to get the lowest uncertainties possible. The second approach is to perform no calculations at all at the time of use. In this scenario, the masses for the deadweight tester are often marked with their corresponding pressure when used with a particular piston cylinder. You simply add up the values on the masses to determine the pressure being generated. This approach is much simpler than the first approach and possibly quicker. One must make a number of assumptions about the environment the pressure balance is being used in. The question then becomes, is it ever acceptable to use a pressure balance in this fashion? Sure, it's quick, but is it right? The answer is yes if the assumptions about the environment are accurate, the level of uncertainty required will support it, and that the equipment being used will support it. Let's look first at the assumptions. As stated before, there are a number of factors that impact the pressure being generated. Perhaps the biggest is the local acceleration of gravity. Pressure is defined as force divided by area. With a pressure balance, the force in question is the force generated by the masses being accelerated downwards by gravity. While the gravity at a specific point in the world is sufficiently constant with time, it can vary from one place to another by as much as 0.5%. For example, standard gravity is defined as 9.80665 meters per second squared. The gravity in the southern half of the United States can be as much as 0.14% different than that. If a deadweight tester is built and configured for use at standard gravity, but is then used in Houston, Texas, all pressure measurements will be off by 0.14%. In addition to gravity, other environmental conditions need to be considered, including temperature and air density. Deadweight testers available on the market today have specifications from 0.1% to as low as 0.008%. As we have already mentioned, accounting for all variables and performing a full calculation of pressure allows for the best uncertainty possible. But at what point is it necessary? As we already saw, local gravity can easily result in an error that is greater than 0.1%. Thus, we need to always account for gravity in some fashion. Depending upon the design of the deadweight tester, it is possible to get performance as good as 0.025% or 0.015% without calculations. For example, the Fluke Calibration P3000 deadweight testers have a specification of 0.015%. This specification can be obtained without performing additional calculations as long as it is used at the gravity specified at time of order, with ambient temperatures between 18 and 28 degrees Celsius, and barometric pressures between 11.6 and 15.2 psi. As a result, no additional software or equipment is necessary. With additional software, it's possible to get 0.008% accuracy with the P3000 deadweight testers. Certain steps were taken in the design and manufacture of these deadweight testers to ensure that this specification can be met without additional calculations by the user. At the time of manufacture, the amount of mass required to generate a given pressure at the customer's gravity is calculated. The masses are then trimmed to this value. Without this trimming, the user has to do some level of calculation. The concept of just adding up the pressures on the masses is completely destroyed. Therefore, Fluke Calibration performs this trimming at no additional cost to the customer. When choosing a deadweight tester, one must pay particular attention to the details behind the specifications. Two manufacturers may offer deadweight testers at the same specification, but they may be making different assumptions on how you are going to use it. The P3000 series of deadweight testers can provide 0.015% performance at pressures up to 20,000 psi, even when operated in the simplest way possible. In addition, they can provide even better performance, as good as 0.008%, when further calculations are performed. For more information, go to www.flukecal.com.